In this video, there are two parts. In the first part, I will give an introduction of artificial intelligence, machine learning, neural network, a typical flow of developing a neural network, and introduce you the most commonly used library in each of the steps. And then, in the second part of this video, I will show you how to build a neural network to predict or classify some things. So first of all, let's talk about what artificial intelligence is. Artificial intelligence, machine learnings, and deep learnings are hot topics nowadays, and these terms seems to be thrown around a lot. To avoid confusion, let me quickly go through the definitions to make sure all of us are on the same page. The earliest definitions of AI was coined by John McCarthy at 1955, who stated that artificial intelligence is the science and engineering of making intelligent machines, especially intelligent computer programs. So after a century, there are so many different definitions of AI, but the main concept is still whole. In essence, AI is a machine with cognitive functions to solve problems that are usually done by us humans with our natural intelligence. So machine learning is one of the many applications in AI. Most recent advance in AI has been achieved by applying machine learning to very large data sets, mainly because of the increasing availability of data, increasing computing power, increasing data transfer rates, and higher density of Internet of Things and smart device. Machine learning algorithms detect patterns and learn how to make predictions and recommendations by processing data and experience, rather than by receiving explicit programming instructions. The algorithm also adapts in response to new data and experience to improve the accuracy over time. Machine learning are often classified by their algorithms that include supervised learning, unsupervised learning, and reinforcement learning. In short, if you train an algorithm with data that also contain the answer, then it is called the supervised learning. And if you train an algorithm with data where you want the machine to figure out the patterns, then that is unsupervised learning. And if you give an algorithm a goal and expect that the machine through trial and error to achieve that goal, then it's called reinforcement learning. And under each of the classifications, there are many types of algorithms such as linear regressions, logistic regressions, support vector machine, random forest, k-mean, q-learning, and so on. And in this video, we will focus on neural network. By definitions, a neural network is a massively parallel distributed processor that is a network which is made up of simple processing units, which are the neurons, and which has the ability to store the knowledge and use the knowledge later on. Neural network resembles the brain in two respects. Knowledge is acquired by the network through a learning process. Interneuron connection strings are used to store the acquired knowledge. So similar to our brain keeps learning by experience and knowledge. And once we acquire the knowledge, our brain can process and apply what we learned later on. So neural network is trained by historical data and the knowledge are stored in the network. After the training, we can provide the relevant information and the neural network will use its knowledge to make an educated guess. But before we move on to the details of a neural network, let's talk about logistic regressions. In some ways, a neural network is a little bit more than several logistic regressions models chained together. So neural networks are somewhat related to logistic regressions, and basically we can think of logistic regressions as only one layer neural network. Although logistic regressions only contains one layer, it still can help us to classify the data categorically, which is a 1 or 0. So there are few steps that we can perform a logistic regressions. Similar to many other machine learning algorithms, we need to initialize the parameters. And in logistic regressions, there are two key parameters that we need to first initialize, which are the weight W and the bias B. And once we initialize these parameters, we will then create a loop to repeat the three main process. In the first step, we work on a forward propagations that will calculate the loss. And in the second step, we work on the backward propagations to calculate the gradient. And once we have the gradient, we will use them to update our parameters. And we continue to repeat these three processes until a certain criteria is reached and that allow us to break the loop. So let's go into the details of each of the steps. To calculate the loss, there are four key steps in the forward propagations. Logistic regressions takes an input and calculates the weighted sum plus a bias. And that's the parameters that we already initialized at the very beginnings. They include W and B. And then the weighted sum is passed on to a sigmoid functions. A sigmoid functions is actually an activation function which outputs 1 when the value of x is large and outputs 0 when the value of x is small. And therefore, after going through these activation functions, the weighted sum will be in a range between 0 and 1, which is the y-hat. Somehow, probabilities is also between 0 and 1, and as a result, this output also can be interpreted as a probability. And later on, you will learn more about the sigmoid functions, which is a very powerful function for us to classify some things, especially in binary classification. So the final step is to calculate the loss in the forward propagations. What we are doing here is actually to assign the loss as an objective functions so that we can optimize these objective functions. There are some mathematical equations behind, but I'm not going through them in details here. The rationale behind this loss function is that instead of minimizing the error, we try to maximize the likelihood. And so this seems like a logical place to start. What it means is that we are trying to maximizing the probability that our model's parameters are correct. And maximizing the likelihood is equivalently to maximizing the log likelihood. And it is also equivalent to minimizing the negative log likelihood. This is because log is a monotonically increasing function. And so, finally, we have the highlighted objective functions that we can try to minimize through the backpropagation. To summarize, after going through a forward propagations, that is the fourth step showing here, we can convert the input x into an output y hat of probability between 0 and 1. And also we can set up an objective functions for our losses. So once we go through the forward propagations, we can start our process in backward propagations. Since the loss functions that we just mentioned only represent one training sample, we need to sum up all the losses from the training samples and take an average on it. And the result is called the cost function. By taking derivative to these cost functions with respect to the two parameters, that is the weight W and bias B, we can calculate the gradient, and this gradient will be used in the next step. So therefore, the objective of having a backward propagations is to help us to calculate the gradients to update our weight and bias. Finally, we can update our parameters. Apart from the gradient djdw and djdb that we just calculate, we can also assign a learning rate to it. And by multiplying the gradients by the learning rate, this magnitude will determine the amount that we move in gradient descent. In other words, this magnitude will determine how much we update our weights W and bias B. These hyperparameters determines how far along the error surface that we travel on each iteration. Bigger values means we go further, which means our weights may converge to the final solutions faster, but it also means that we may overshoot that solution. A higher learning rate means that we should move W and B more on each step, and the change we make in our parameters is the learning rate times the gradient. A quick summary here, just to show what we have gone through. In the first step, we work on a forward propagations, and that will calculate the loss. And then in the second step, we work on the backward propagations to calculate the gradients. And once we have the gradient, we will use them to update our parameters. And we continue to repeat these three processes until a certain criteria is reached, and that allows us to break the loop. Now we can put everything inside a loop in order for us to continue to improve the rate and bias. Here we need to decide how many epochs or iteration or steps that we want to update our parameters. The number of epochs is another hyperparameters. On the other hand, there are many ways to determine when to stop the gradient descent process. We will mention some of them later in this video. So here I would like to mention that we call things like learning rate and epoch like a hyperparameters. These are parameters that are not part of the model itself, but still can be used to improve our result, and which are very important concepts that we will mention later as well. Previously, we had talked about the logistic regressions, and we saw how this model corresponds to the following computational graph, where we input the feature x and the parameters w and b's that allow us to compute the weighted sum, and sometimes the weighted sum is referred to z. The z is then used to compute a, or the output y hat that we used previously. But don't worry about that because these two terms means the same thing. And then we can compute the loss functions L. And here, x, w, b, and a are all vectors. And this simple change is actually called the vectorization, which is used to speed up the computational process. As I mentioned before, the concept of neural network and logistic regressions are very similar. But of course, neural network is much complex in reality. But you can think of that neural network is little more than several logistic regressions models stacking together. And to be specific, a neural network can be formed by stacking together a lot of little sigmoid units. So let's see how we can do this. Previously, this node corresponds to two steps of calculations. The first, we compute the z value, and second, we compute the a value. And in this neural network down below, this stack of nodes will correspond similarly. That is two steps. One is to compute z, and then compute a. And we have one more layers in this neural network. So another node in the second layer will correspond to another z and another a calculations. In the neural network, the training process also involves three key steps. They include a forward propagations to calculate the loss, a backward propagations to calculate the gradient, and using a gradient descent to update the parameters. Now we can also put everything inside a loop in order for us to continue to improve the rate and bias in the neural network. So let's take this simple network as an example for us to understand how forward propagations, backward propagation, and gradient descent work. So here, let's go through the calculations for the first node in the first layer. Similar to logistic regressions, there are two steps of computation. The first is to compute z, which equals to w transpose x plus b. Since all quantities are associated in the first node, in the first hidden layer, the notation here we used is that the square bracket 1 present the layer and the subscript 1 present the first node. Once we calculate z, then we can go to the second step that we can compute a11 by applying the sigmoid functions to z11. Now let's move down to the second node in the first layer in the neural network. Similar to the node 1, this little circle represents two steps of computation. The first step is to compute Z12, which equals to W12 transpose X plus B12. And then A12 equals to the sigmoid of C12. So we are done in the layer 1. Let me put the Z equations and A equations side by side. Just make sure the notation and the understanding are all clear here. Z, W, B, and A are all vectors. Say for example, W11 is a vector and that can be transposed and times a vector X. And the sigma function here is applied element-wise to the Z vector. The concept here is very important because when you're implementing your neural network, you don't want to do the computation inside a for loop because it is very inefficient. So what we are going to do here is to take all the equations in layer 1 and vectorize them. So let's see how we can do that. On the left-hand side of the equations, we take out all the Z11 and Z12 and stack them into a vector. And then on the right-hand side of the equations, similarly, we take out the weight vector W and stack them together into a matrix. By doing so, we will end up with a 2 by 3 matrix in this example. Here, let me explain a little bit more. I expand a little bit of the W11 vector and grade the nodes to illustrate each of the elements inside the matrix. So you can see that in the first element of the matrix, W11, X1, is actually representing the weight between X1 and the first node in the first layer. And this is similar to W11X2 and W11X3, which represent the weight between X2 and X3 and the first node in the first layer. So here you can see because there are 3 inputs in the previous layer, we will have 3 weight parameters to connect them to the first node. And similarly, we will have 3 weight parameters to connect them to the second node. So it ends up we will have a 2 by 3 matrix in which the number of rows equals to the nodes in the current layer and the number of columns equals to the nodes in the previous layer. So now we can take this 2 by 3 matrix and multiply it by our input features x1, x2, and x3. And finally, we stack the b11 and b12 into a B vector. So we have just shown how we can vectorize the hidden layer 1. And for the notation, we just combine all the vectors and matrix and remove the subscripts to represent them as their corresponding vectors and matrix. Therefore, in this case, we will have C1 to present the vector C, and W1 to represent the rate matrix W, and similarly for X and B. So let's not forget the sigmoid activation function in the layer 1. Similarly, we can stack A into a vector A. And this is going to be the sigmoid of Z1, where now is the implementation of a sigmoid functions that takes in the 2 elements of Z and applies sigmoid function element-wise to Z11 and Z12. With similar vectorization, we can also represent layer 2 as by the highlighted equations in such a way that the overall calculations is more efficient and more effective. Remember, we have a C1, which is a 2 by 1 vector. And after the element-wise sigmoid activation function, we should still have a 2 by 1 vector A. And W2 in this case, it should be a 1 by 2 matrix because of 2 neurons in the previous layer and 1 neurons in the current layer. As a rule of thumb, the number of rows in W2 should be the number of neurons in current layer, while the number of columns in W2 should be the number of neurons in previous layer. And this logic can be applied for all the layers inside the neural network. And then we can add a 1 by 1 matrix B to the W2 and A1. Hence, Z2 is going to be a 1 by 1 matrix. And because of Z2 is a 1 by 1 matrix, after the element-wise sigmoid activations, the output A2 should be a 1 by 1 matrix as well. After going through the hidden layer 1 and hidden layer 2, this will give us the result y hat. And also this will give us a loss functions for each of the sample. And then we can feed in all samples through this forward propagation process and calculate the cost for all the samples. Similar to the logistic regressions, we can take the derivatives of cost functions with respect to weight W and bias B at each of the layers to get the gradient. And then by using the gradient multiplied by the learning rate, we can update the parameters W and B. The derivatives here of these backpropagations is one of the most complicated maths that is involved in neural network. The main reasons are because of the number of chain rules calculations involved is proportional to your numbers of layers. In addition, gradient descent is only one of the learning algorithm to be used for updating the parameters. Unfortunately, we don't have to derive it from scratch because many Python libraries provide these software to perform the learning. So what we need to learn is to know which softwares can provide the better estimates in different problems. Once we have these three basic steps, that is the forward propagations to calculate the loss, the backward propagations to calculate the gradients, and gradient descent to update the parameters, we can continue to improve the weights and bias. So similar to logistic regressions, we can put everything inside a loop in order for us to repeat these three processes until a certain criteria is reached and that allow us to break the loop. As mentioned before, we need to decide how many epochs or iterations or steps that we want to update our parameters, and the number of epochs is another hyperparameters. And there are many ways to determine when to stop the gradient descent process, and we will mention some of them later in this video. So let's move on and try to understand how we can develop a neural network. Typically for a data science project, it will involve the data collection, data exploration, data preprocessing, model development, and model evaluations. So similarly, in order for us to build a nice neural network, generally speaking, we need to collect data, explore and processing them, and then we need to extract the features and label that can fulfill the objective of this project. The features are the inputs, which are the attributes that we think are important for our neural network to learn in order for it to predict the output, which here are the labels. And of course, these labels need to be well selected in order for us to fulfill the objective. That said, we should also take our objectives into considerations to collect relevant data at the very beginning. And most of these steps can be done by pandas. Then, then we can split our dataset that contains the features and labels into the training, development, and testing set, so as to help us to train our models and evaluate how well the trained model performs. And sklearn and keras can help us to perform these tasks. Before we pass the trained and development set to our neural network model for training, in many cases we will normalize our data. These normalizations is mainly lead because sometimes our features have many different ranges, and we want to normalize them in order for us to speed up the whole training process. Because sklearns return the training, development and testing sets in NumPy and the array, so we generally will just use NumPy functions here to help us to normalize the data. Once we normalize the datasets, we can then design our network architect. The neural network model and the architect of a neural network determines how a network transforms its input into an output. The term neural network architect refers to the arrangement of neurons in the layers, the connections patterns between layers, the activation functions, and the learning algorithm. By constructing a nice network architect, the performance of neural network can be much better. And the next thing we need to do is setting the hyperparameters. Being effective in developing a neural network requires that we organize the parameters as well as the hyperparameters nicely. Some common hyperparameters include the learning rate based on the learning algorithm that you selected in the network architect, the batch size, the number of epochs, and any other early stopping criteria to prevent you overtraining your model. Once we decide the model architect and assign the hyperparameters, we are ready to train the neural network. Training involves making predictions based on the current states of the models, calculating how incorrect the prediction is, and updating the parameters W and B of the network to minimize this error and to make the model predict better. We repeat this process until our models have converged and can no longer learn. In Keras, there are two main functions involved, including compile functions and fit function. Developing neural network is highly iterative. Therefore, before we have the final model, normally we need to use our development and testing datasets to evaluate our trained model. The development dataset would be useful to determine how well your trained model perform and whether there are any overfitting or underfitting issues, while the testing dataset will provide you an additional unbiased evaluations to your trained model. If the evaluation in the model set, development set, or testing set are not good, we always need to go back to the previous steps to refine our models again. Both development and testing set evaluations can be performed with the use of Keras. As mentioned, developing a neural network is highly iterative, and it has many processes based on random selection and hyperparameters settings. One obvious example is that when we split our data into training set, development set, and testing set, the process is random sampling. So sometimes we will train a field model and average the results, or sometimes we will combine many different types of neural network models in order to get a better prediction. This process is called ensemble learning, which very often can reduce the error and improve the accuracy of our model. In Python, a file is categorized as either text or binary file. Text files are structured as a sequence of lines, where each line includes a sequence of characters, such as HTML, XML, and TXT files. And a binary file is any types of files that is not a text file, such as PDF, image files, and video files. Because of their natures, binary files can only be processed by an application that know and understand the file structure. In other words, there must be some applications that can read and interpret the binary files. In order for us to work with a text file in Python, we can use the built-in open function. For binary files such as Excel, CSV, and many other types of files, we can use Panda. Functions like the pandas with CSV, with Excel methods enable us to work with files effectively. And we can easily collect data by using these two methods. If we use pandas functions to extract data from our text file or binary file, the data will be formed as a data frame. And pandas further allow us to perform various data manipulation operations. And we can perform some descriptive functions with the use of pandas functions. In short, descriptive statistics help us quickly understand the features of a specific dataset by giving short summaries about the samples and measures of the data. The most recognized types of descriptive statistics are cons, sums, mean, median, mode, standard deviations, mean, and mass. But to me, this is just the basic things that we need to know about the dataset that you've just pulled out. And in most of the time, we should already have some ideas about what kind of data that we are going to collect from the database. Therefore, other than the descriptive statistic functions that were performed by using the pandas, we can also perform some other statistical functions such as percentage change, covariance, and correlation in order for us to have a more understanding about the data sets that you just pull out. Having a correlation coefficient matrix is very important in developing a good neural network. The reason is mainly because correlation coefficients matrix can give us a sense of how strong that our input features are related to our output labels. And in most of the times, we should include the features that have very strong correlation coefficients with your output labels. So to me, establishing a correlation coefficient matrix is a very important step that I never skip. Instead of applying statistical functions to the whole dataset, sometimes we want to split the data into group and apply a statistical functions to each of the group in order for us to analyze our data in a meaningful sense. So group by in pandas can help us to do this easily. And group by is a pretty simple concept. We can create a grouping of the data and then apply a function to each of the group. When we refer group by, it mainly involves one or more of the following steps. They include splitting, applying, and combining. So splitting is a process in which we split data into group and by applying some conditions on the dataset. And applying is a process in which we apply a functions to each of the group independently. Combining is a process in which we combine different data sets after applying the group by and result into a data structure. After having some understandings about the collected data, we can now deal with some practical issues. For example, working with multiple data frames, dealing with missing data, and dealing with time series data. In many real-world situations, the data that we want to use come in multiple files. We often need to combine these files into a single data frame in order for us to analyze the data. The pandas package provides various methods for combining data frame, and the most commonly used methods are merge and concat. Sometimes we also face missing data issues. Missing data can occur when no information is provided for one or more items or for a whole unit. Missing data is always a problem for machine learning and data analytics. Very often, it causes a lot of issue in the accuracy of model predictions because of poor quality of the data caused by the missing values. In this area, missing value treatments is a major point to focus in order for us to make our models more accurate and valid. In pandas, if we have more than enough samples, we can just apply the drop NA functions to drop the samples that contain the missing data. But when we have a situation that every single data is important to us, then we might want to apply fill NA or interpolate functions to fill in the missing data in order for us to keep as many samples as we could. Apart from working with multiple data frames and dealing with missing data, encountering time series data is very common. I like using pandas to deal with it because it contains extensive functions and features for working with time series data. One commonly used function is to datetime. When CSV or Excel file is imported and a data frame is made, the dataframe objects in the files are with as a string object rather than a datetime object, and hence it is very tough for us to perform time-related operations. So by using toDateTime function, we can easily convert the date and time from text strings in pandas. And once we have the data frame objects, we can have further analysis on the data. After going through the data collection, exploration, and pre-processing steps, We should come up with a Panda tables like this. The number of rows of the Panda data frame represent the number of samples that we have, and the number of columns of the Pandas data frame represents the number of features and number of labels. Here, the diagram is just for illustrative purpose. It doesn't mean we only can have one columns for labels. Sometimes, if we have multi-class classifications, we certainly will have more than one column. However, the data frames that we are going to have should be more or less the same as what we show here. To extract the features and labels from the tables, there are two commonly used methods to extract the data in pandas, which are .loc and .iloc methods. .loc is primarily label-based, and .iloc is primarily integer-based. Here, I just quickly introduce those commonly used functions in pandas for each of the steps. And if you want to know more, please feel free to watch my pandas series in my channel. For each of the methods that I mentioned, I have detailed explanations and examples over there. Developing neural network is a highly iterative process. We need to prepare the data, develop the model, and evaluate the model. If the evaluation is not satisfied, we might need to go back to prepare the data again or develop the model again and perform another evaluations. And hopefully, after going through this process for many times, we could come up with a nice neural network. Therefore, setting up our data well in terms of the training, development, and testing set can make this iterative process much more efficient. As mentioned before, the number of rows are the samples that we have. And in this step, normally we will split the whole dataset into three portions that includes the training set, the development set, sometimes this is referring to the validation set, and testing set. The workflow here is that we first train our neural network with the training set, and then we use the development set or the validation set to determine which one of the many trained neural network performs best. And then after many iterations, when you are comfortable with the results estimated by the final models, we will take this best model and have a final evaluations with the use of the testing set in order for us to have an unbiased estimate of how well this final trained neural network performs. What do we mean for unbiased estimate? Here, because the final neural network is determined by the training and development set, so the trained model have never come across this testing set. Therefore, when we fit this testing set into the final neural network and evaluate its performance, such estimations is unbiased. Sometimes it might be okay if we do not have any testing set, because the goal of the test set is to give us an unbiased estimate of how well our neural network performs. But if we don't need this unbiased estimate, it might be okay for us not having a testing set. But for the sake of completeness, let's just assume we want to have our testing set for unbiased estimate. In Python, we can use two steps to split the data into the training and development set. The first step here is to use the sklearn train test split functions to split the data into the training and development set and testing set. The second step here is to use Keras validation split functions, that is under the split functions, to split the training set and development set. Because it is under the split functions of the Keras, so practically we will set these parameters in the later neural network training step. Once we split the samples into the training set, development set, and testing set, we can then normalize these data to speed up the training. The step here is particularly important if the input features come from different scales or range. Say, for example, if you have one feature ranging from 1 to 10, while you have another features ranging from 1 to 10,000, then normalization would probably help to speed up the process. In the previous step, the function train test speed from sklearned will return us a numpy array objects. Therefore, here we need to use numpy to help us to normalize the data. A typical way to normalize the data is that we first split the raw data into training and test sets, and then we normalize the training set and save the normalization's parameters. And then finally, we use the training normalization parameters to normalize the testing set. So in the first step, we split the data, which is already done by sklearn function. And then we normalize our training and development sets. Let's say, for example, we use zero mean and unit variance normalization. These techniques transform their features to a random variable with a mean value of 0 and variance of 1. And here it is assumed that the individual components of the features vector are normally distributed, which is fairly valid in most of the case if your dataset is large enough. So what we do here is to extract the mean and standard deviation from the training and development set, and then we subtract every sample by the mean, which move all data from a certain mean value to mean 0. And then we divide it by the standard deviation, which in turn standardize the range of the features and labels. So as a result, we will have a normalized training and development set. Here, we just save the normalization's parameters. And finally, we use the saved mean and standard deviations to normalize our testing set. And we will have the normalized testing set, and that's it for the normalization step. Before we move into the details of the network architecture, let's talk about the bias and variance. Because whenever we discuss the model results, it is very important for us to understand the errors, which are bias and variance. There's always a trade-off between a model's ability to minimize the bias and variance. Gaining a proper understanding of these errors would help us not only to build an accurate model, but also to avoid the mistake of overfitting and underfitting. Simply speaking, the goal of any unsupervised neural network algorithm is to achieve no bias and no variance. Therefore, we always need to assess the bias and variance. And these assessments help us to check how well our machine learning models learns and how well our trained models predicts and generalize to the new data. Generally speaking, bias is the difference between the predictions of our models and the correct values which we are trying to predict under training data. Model with high bias pays very little attention to the training data and oversimplifying the models, and it is a sign of underfittings. And once we develop our model, we will use the model to perform predictions with the use of the data in development set and testing set. So generally speaking, variance is the error between predictions and correct value under development set and testing set. Model with high variance pay a lot of attention to training data and does not generalize on the data which it hasn't been seen before. As a result, such training models perform very well on training data but has a very high error rate on development set and testing sets, and which give us a sign of overfitting. To achieve a low bias and low variance models, we can start setting up a network architect. In general, the term neural network architect refers to the arrangement of neurons in layers and the connections patterns between layers, activation functions, and learning algorithm. The neural network models and the architect of a neural network determines how a network transforms its input into an output. Although developing a neural network is normally through trial and error, there are still some commonly used approach. For layer and neuron, there are two widely used approaches. One is starting from underfitting, while one is start from overfitting the model. The idea of underfitting is to move from a shallow network, which has only one or two layers and not too many neurons, to a deep network, which contains more layers and neurons. The rationale behind this approach is that we want to improve both bias and variance progressively. The second approach is starting from a deep network and removing layers and neurons progressively to achieve the final model. And the rationale behind this approach is that we want to achieve a fairly low bias at start and reduce the variance progressively towards the bias. Generally speaking, I personally prefer using the overfitting approach in such a way that the bias is low enough and my focus is just to fine-tune the models to achieve a low variance as well. After arbitrarily assigning layers and neurons that help us to learn to map samples of inputs to outputs, we need to decide which activation functions that we are going to use in each of the layer. The activation functions here is responsible for transforming the subdivided input from the node to an output for that input. Therefore, in the network architect, we do not need to define the activation functions in input layer, and we only need to define the activation functions for both hidden and output layer. The simplest activation functions is referred to as a linear activations, where no transform is applied at all. A network comprised of only linear activation functions is very easy to train, but cannot learn complex mapping functions. So we don't use linear functions in the hidden layer at all. However, linear activation functions are still used in the output layer for networks that predict a quantity in regression problems. Nonlinear activation functions are much more preferred as they allow the nodes to learn more complex structures in the data. In other words, the purpose of the activation functions is to introduce nonlinearity into the output of a neuron. Traditionally, a very widely used nonlinear activation functions is the sigmoid activation function. In the logistic regressions model, we already discussed about the sigmoid activation function. But indeed, there are many more other choices, and sometimes other activation functions can work better for our models, such as value, 10H, linear, softmax. In short, for hidden layers, sigmoids, 10H, and values are commonly used activation functions, while for output layers, sigmoids, softmax, and linears are the commonly used activation functions for different purposes. Let me introduce them to you one by one. Sigmoid function is like a S-shaped curve that map into values to output values between 0 and 1. And functions is differentiable. That means we can find the slope of the sigmoid curve at any 2 points. The function is also monotonic. That means it is increasing only if we go along the curve from left to right. However, the function's derivative is not monotonic, and the derivative is larger in values around the 0 in x-axis. Since probability of anything exists only between the range of 0 and 1, as we mentioned before, sigmoid is very often a right choice to predict the probabilities as an output. Therefore, it is suitable to be used in the output layers when we apply sigmoid functions at the outputs, that is a binary classifications. And there are generally two situations that we might find sigmoid functions useful. The first situation is that if we want our output value between 0 and 1, we can use sigmoid at the output layer. The second situation is that when we are working on a binary classification problem, we can use sigmoid functions in hidden and output layers. However, other than that, sigmoid function is not a preferable option because we have better derivation functions, and I will talk about them in a minute. Before I introduce you the better alternatives to sigmoid derivation functions, let's talk about the softmax functions. The softmax functions is a more generalized logistic derivation functions. Softmax functions does not only maps our output functions, but also maps each output in such a way that the summations is equal to 1. Therefore, softmax functions is mainly applied in the final layer of neural network for multi-class softmax classification. As mentioned before, we have better alternative to sigmoid derivation functions. 10H is also like logistic sigmoid, but better in practice. 10H is S-shaped, differentiable, function is monotonic, but its derivative is not. But one most important feature is that the range of the 10H functions is from -1 to +1. Remember that when we normalized our data before, so our data is centered around 0. And the range of the 10H functions is -1 to +1, and that can help mapping the negative inputs more strongly in negative regions. And also the 0 inputs will be mapped near 0 in the 10H graph. Also, 10H has a steeper slope around 0, and that can speed up the learning process. Therefore, in practice, 10H is always preferred over sigmoid functions. Although 10H is better than sigmoid functions in practice, there are still some problems in both 10H and sigmoid functions that they suffer from vanishing gradient problems. As you can observe that when the sigmoid and 10H functions value are either too high or too low, the derivative becomes very small. And because the tails of these two functions are plateau, and these will make the learning very difficult or very slow at these two extreme points. And this is what we call vanishing gradient problems. And this leads to poor learning, especially for very deep network. So another choice in developing neural network, which is called the rectified linear unit value, that can help us to solve the vanishing gradient problems. A value functions give an output x if x is positive and 0 otherwise. So the derivative is 1 when x is positive, while the derivative is 0 when x is negative. And therefore, this avoids and rectifies vanishing gradient problem. When implementing a value functions, technically, when x is equals to 0, the derivative is not very well defined. But when you're implementing it in a computer, if it will give you a 0 float number, so you don't have worry about it. Apart from avoiding the vanishing gradient problems, value is also less computational expensive than 10H and sigmoid because it involves simpler mathematical operations. Therefore, almost all deep learning models nowadays use value. But its limitation is that it should only be used within hidden layers of a neural network model. And also, the issue is that all the negative values become 0 immediately, which decrease the ability of the model to fit or train from the data properly. That means Any negative input given to the value activation functions turns the value into 0 immediately in the graph, which in turn affects the resulting graph by not mapping the negative values appropriately. And leaky value is another way to solve these problems, but I will not go through these in details here because this is not as commonly applied as value. To give you a very quick summary, for hidden layer, if you're not sure what to use in your hidden layer, it is almost default to use value, especially for a very deep network. But if your problem has negative inputs and that you need to take care of, 10H might be an alternative, but only in a less deep network. For output layer, if you're working with a classification problem, sigmoid and softmax are the best options. And for prediction problems, we aim to predict the output of a continuous values. Contrast this with a classification problem, where we aim to select a class from a list or classes. Linear layer is always preferred. The last thing that I want to talk about for the new network architects is the learning algorithms. Remember previously we discussed about that we've used forward and backward propagations to derive a cost functions for neural network. And then we will use an algorithm like gradient descent to minimize that cost functions. When we have a very large training set, gradient descent becomes a computationally very expensive procedures. And in Keras, there are some other learning algorithms that can be used to speed up the gradient descent searching, such as SGD, SGD with momentum, RMSPOP, and ADAM. As mentioned, gradient descent is computationally very expensive procedures in a deep neural network. The reason is because in a typical gradient descent optimizations, it takes the whole dataset into the considerations when we minimize the cost functions. Although using the whole dataset is really useful for getting to the minima in a less noisy or less random manner, but the problem arises when our dataset gets really huge. This problem is solved by stochastic gradient descent, that is SGD. In SGD, instead of taking the whole dataset into considerations, it uses only a single sample to perform each iteration. The sample is randomly shuffled and selected for performing the iterations. In SGDs, since only one sample from the dataset is chosen at random for each iteration, the path taken by the algorithm to reach the minima is usually noisier than your typical gradient descent algorithm. But that doesn't matter because the path taken by the algorithm does not matter as long as we reach the minima and with significantly shorter training time. One thing to be noted is that as SGD is generally noisier than typical gradient descent, it usually took a higher number of iterations to reach the minima because it's randomness in its descent. Even though it requires a higher number of iterations to reach the minima than typical gradient descent, it is still computationally much less expensive than typical gradient descent. Hence, in most scenarios, SGD is preferred over batch gradient descent for optimizing a learning algorithm. SGD with momentums is another learning algorithm that it shares similar concepts with SGD, except that we introduce a velocity to it to speed up the whole process. Therefore, instead of using only the gradient of the current step to guide the search, momentum also accumulates the gradients of the past steps to determine the directions to go, so as to reduce the oscillations or noise around the pathway. The advantage of momentum is that it makes very small change to SGD, but provide a big boost to speed of the learning. SGD and SGD with momentum just apply equal learning rates for all our parameters. So all of our parameters are being updated with constant factor. However, this might not be the faster way to solve the problem. And periodically, we can speed up the process if we know which directions to accelerate and which to decelerate. And we can also speed up the process if we can adaptively tune the learning throughout the training phases. There is a higher learning rate at the start and a slower learning rate when approach the target. Several learning algorithms share this concept, such as RMS Pop and Adam. When RMS Pop receive big updates, it will have their effective learning rates reduced. When it receives small updates, it will have their effective learning rate increased. This way, we can accelerate the convergence by accelerating per parameters learning. In addition, RMS pops pose a decaying rate to control the learning rate, which make it better choice than the Ada Gray learning algorithm. Last but not least, we have Adam learning algorithm, which is a recently proposed and currently state-of-the-art learning algorithm. It is an improvement upon RMS pop by adding momentums to the update rules, combining the best of the both momentum and adaptive learning characteristic. In practice, as a rule of thumb, if you have a very small dataset, it would be recommended to try SGD or SGD with momentum. But if you have a medium to large dataset, it would be recommended to try RMS Pop and Adam. Developing a neural network is highly iterative through trial and error. There's no right or wrong approach, but hopefully we can work it in a systematic and logical way to speed up the whole process. Therefore, once we set up an initial network architect, we definitely will come back to this step again and refine the setting again and again until we are satisfied with the result. And the next things we need to do is setting the hyperparameters. Similar to the network architect, we probably will go back to this step again and fine tune the setup. The reason is mainly because your datasets is probably changing and updating that, and that will affect your features and labels from time to time. So at least once every several months, we need to retrain our models or re-evaluate our results. Being effective in developing a neural network requires that we organize the parameters as well as the hyperparameters well. Before we go into the details, let's talk about a bit of the term parameters and hyperparameters. So in neural network, the parameters of our models include W and B, and which is what we want to optimize. And these two parameters is out of our control. So what we can control is actually the hyperparameters, which are the parameters that we can modify in order for us to control the output of parameters W and B. And so as a result, this is called hyperparameters. We have just discussed about the neural network architect, and some of the hyperparameters will depend on the choices of our network architect, while some of the hyperparameters will not. Say, for example, depends on the learning algorithms that you pick. We need to assign the learning rate, momentums, or decay rate appropriately. Other common hyperparameters include the batch size and number of epochs. Typically, if you have a very large dataset, you would probably need to divide your datasets in batch for speeding up the whole process, the whole training process. But if you have a very small dataset, you can just ignore these hyperparameters. And you also need to define the number of epochs that you want your training model going through. So, however, the choice of the number of training epochs could be a problem. Too many iterations can lead to overfitting of the training dataset, whereas too few may result in an underfit model. So in order to avoid this problem, we will use early stopping criteria to help us. Early stopping is a method that allows you to specify an arbitrary large number of training epochs and stop training once the model performance stops improving on the development set. Carriers provide you the flexibility to choose which quantity that you want to monitor and how many epochs with no improvement that you will wait for and stop the training. Now we can start training our model. Once we have decided the model architect, we can come to this step and to start to train the model. Training involves making a prediction based on the current state of the model, calculate how incorrect the prediction is, and updating the parameters W and B of the network to minimize this error and make the predictions much more better. We will repeat this process until our models has converged and can no longer learn. In Keras, we need to compile the model before we train it, and there are three key parameters to be chosen for this process that includes optimizer, loss, and metrics. The optimizer is the learning algorithm that we discussed before, such as SGD, SGD with momentum, RMS pop, and Atom. For small to medium datasets, we can use SGD and SGD with momentum. While for medium to large dataset, we can use RMS pop and Atom. The second parameter that we have to assign for the compile functions is the loss. Loss is the objective functions that we have for the training. Remember in the logistic regressions, our objective functions is to minimize the negative likelihood loss or the cost entropy loss. A function that is defined here is to calculate a loss value that when the training process and then attempts to minimize by tuning the network parameters. Say for example, for binary classification, we can minimize the binary cost entropy loss. And for multi-class classification, it depends on how you arrange your labels. So if your labels are one-hot encoded, you can use categorical cost entropy. But if your labels are integers, you can use the sparse categorical cost entropy. And for predictions, we normally just use the mean square error. Mathematically, the larger the mistakes results in more error than smaller mistake, meaning that we will punish more for making larger mistakes in such a way that our model is more stable and robust in predictions. And the last parameter is the metrics, which is used to evaluate the performance of our models in the training and development sets. For binary classifications, we can use binary accuracy to evaluate the model. For multicast classifications, it depends on how you arrange your labels again. So if your labels are one-hot encoded, you can use categorical accuracy. But if your labels are integers, you can use sparse categorical accuracy. For predictions, we normally use mean square error, mean absolute error, or MAPE, that is the mean absolute percentage error, to evaluate the performance of our model. Once we compile the models, we can then use fit functions to train the model. Depending on the size of your dataset, this is the methods in which most compute cycles will be spent. Here, X represents the features in training and development sets, while Y represents the labels in the training and development set. The validation speed is used to speed the training and development set. For example, if we set it as 0.1, then we are going to have 10% of data that will be used for development set, and while the remaining 90% will be used for training. At the end of each epoch, we use the development set to evaluate how well the model is learning. If you still remember, I mentioned it before, there are two steps involved for us to split the data into training, development, and testing set. The first step is to use sklearn functions to split the data into two sets. One is training and development set, and the other is testing set. And the second step is actually hidden here, that is in the keras validation split functions. And that will allow us to further split the training set and development set. And then we can determine how many epochs that we want to train our network. The next thing that we need to assign is the batch size. In each training iterations, batch size is used to determine the number of samples from your training data that will be used to compute the loss. And the weights and bias are updated once based on these loss value. So the larger the batch size, the less computational effort that you will spend, and hence the faster your training will be. Normally, we repeat training using the dataset based on the number of epochs. On the other hand, we can also stop training when a monitored criteria has stopped it improving. And we can set these early stopping criteria in the callback. For example, we can stop it when the validation accuracy stabilizes between consecutive epochs, showing that the model is not in training anymore. However, epoch should not be a constraint to our model. In general, we will just set it to a very large numbers and use these callbacks to stop training our model so as to avoid overfitting or overtraining. Once our model is trained, we need to evaluate how good or how bad it is. In the previous step, when we use the fit function, the argument validation speed allow us to automatically reserve parts of our training data for validation. And based on the metrics that we assign, we can evaluate how well our model performs in the development set. For additional evaluation, we can use the testing set. Remember, we speak with the use of functions in sklearn before. And in this very last step, we can use this testing set to perform an unbiased evaluation over our trained model. In keras, we can use the evaluation function to calculate the loss value and matrix value that we assigned for the model before. As mentioned many times, developing neural network is highly iterative. Therefore, if the evaluations in the training set, development set, or testing set are not good, we always need to go back to the previous steps to fine-tune our models again and again. Here are two practical advice. If your model have high bias, that is high training error, your model is likely suffered from undertraining or underfitting. In that case, there are several approaches commonly used to solve the problem. For example, you can go back to the network architect and try to increase the size of your network and increase the number of epochs or find a more complex architect. And on the other hand, if you already achieve a low bias, but yet still a very high variance, that means your model is likely suffered from overtraining or overfitting. In that case, you might need to go back to the first step to collect more data, or you can go back to the network architect to work out some regularizations or find a simpler architect. Now we come to the final part, the final model. Because machine learning is highly iterative, it has many processes based on random selection and hyperparameters. One obvious example is that when we split our data into training set, development set, and testing set, the process is random sampling. So very often we will train a few models and averaging the result. Or sometimes we will combine many different neural network models in order for us to get a better predictions. And this process is called the ensemble learning. In this part, I will only introduce those methods that do not distort our flow from developing neural networks significantly, and those models that can be easily implemented. Let's take a look for a few simple but powerful techniques, namely mass voting, averaging, and weighted averaging. The mass voting methods is generally used for classification problem. In this technique, multiple models are used to make predictions for each data point. The predictions by models are considered as a vote. The predictions which we get from the majority of the models are used as the final predictions. In other words, you can consider this as taking the mode of all the predictions. Similar to the mass voting techniques, multiple predictions are made for each data point in averaging. In these methods, we simply take an average of predictions from all the models and use it to make the final prediction. Averaging can be used for making predictions in different type of prediction problems. In other words, you can consider this as taking the mean of all of the predictions. Weighted average is an extension of the averaging methods. However, instead of giving same weights to each of the models, all models will be assigned different weights, defining the importance of each of the prediction. And we will calculate the averaging based on their importance and their weight. Here is a question. If you create all the models on the same set of data and combine it, will it be useful? There's a high chance that these models will give very similar or same results even they are getting the same input. So how can we solve their problems? So in order for us to combine the results of multiple models to get a more generalized result, we will apply the bagging concept. And one of the techniques is bootstrapping. Bootstrapping is a sampling technique in which we create subsets of observation from the original datasets and with replacement, so that the size of the subset is actually the same as the size of the original set. The simplest way to apply these methods is to create a loop and provide different random seed in the sklearn functions, train, test, speed in each of the cycle. Because the model run in parallel and are independent to each other. If you have enough computational power, the models can be run parallel without disturbing others. The final predictions are determined by combining the predictions from all the models. Ensemble methods are very powerful techniques. The main reason is because we don't need to spend too much effort, yet we still can achieve a more stable, robust, or even more accurate solution than a single solution from single model. And you could imagine even the smallest amount of improvement in the accuracy of machine learning algorithm can be something truly variable for many industries, such as healthcare and energy sectors. But for now, for what we covered, we should be able to develop a very nice neural network. So, after having some basic understanding about the flow for developing neural network, let's go through an exercise to see how we can follow the flow diagram step by step to build a neural network. So let's get started. So the first thing that I need to do is just to import pandas as PD because in the basic flow for developing neural network, the first four steps are just using pandas. So here I just import pandas to complete the first four steps. They include the data collection, data exploration, and data pre-processing. So for the dataset, I already download two sets of data from Yahoo Finance. The first set is the Hang Seng Index, and the second set is the Shanghai Index. So we can use PD docs with CSV to collects the data, and I have a header inside this file that is in the first row. So header equals to 0. The second data set is the Shanghai index. So let's print out the data types, print out the shape, and also print out the first few columns of these data sets in order for us to have some understanding. So the first is Hansen index, and then we want to print out the shape as well. And let's see the first few rows. Also, let me print out the Shanghai index for the first few column. So because we just use the with CSV file to pull the data from Hansen index CSV and Shanghai index CSV, so all of the data will become an object type that is a data frame object. And so we have to convert them before we perform any data processing later on. So we have about 7,000 samples and about 7 columns for each of the table. And so we contains the date, the open price, high price, low price, close price, adjusted close price, and volume in Hansen index data frame. And similarly, for the Shanghai index data frame, we have a similar column. The first thing we need to do is going to combine these two tables in order for us to create a table that contains the required features and labels. So the first thing we need to use the date here to combine these two data frames together. However, because date is a string type right here, so we have to use the toDateTime function to convert them to a datetime type object. So let's see how we can do that. So we are going to convert the date column. That should be equals to the pandas dot toDateTime function, and that is the HSI date column. And then the format, we need to follow the format. So the format is this one, that is the date, month, and years. So we just follow that the format, that is the date, that is the month, and that is the years. So similarly, we can convert the date in Shanghai index as well. But here you can see that the format is different. So we have the year go first, and then a hyphen, and then a month, and then another hyphen. Okay, let's see what we have. So now we can see that the date type has been changed to a datetime object. And now we can merge the two tables together according to the date. So I'm going to perform a left merge. That means the Hansen index here is the main table, and then Shanghai index just have to merge with them. So we have a pd.merge, left equals to Hang Seng Index and right equals to Shanghai Index. And then how, just like what I mentioned, that is the left merge. That means Hang Seng Index tables will remain the same for all of the rows. So, and then left on is the date, because I just convert the date in both table into a datetime object. So the right on is also the date. So we are going to have a merge the data frame. Maybe we can just print out the first 3 row to show you what we have. Here you can see that because we just use the left merge, that means the Hang Seng Index will be the main table. And then if there's no data from the Shanghai Index, we will just have an NAN for the corresponding date. So never mind, we can continue to move on because we still have to deal with the missing data later. Because the date time objects cannot be used for neural network training. So, however, I still want to keep the years and month as the features. So in order for us to do that, we can use the dt function dot year and dt function dot month to create 2 additional columns. That is our features. The first feature is the year, and then the second feature will be the month. Okay, so we are going to take this date column and then just take out the year and store everything in this column, year column. Similarly, we just take out the month from the daytimes column and create a new column month to store them. Here we can just drop the date because we are not going to use it for as our features. And then the exit is equals to 1, and that means we just drop the column and then in place true. Okay, that's good. So here you can see that we just create 2 additional columns that contains the years and the other contains the month for our features. And then we also just drop the date columns because that would not be useful in developing our neural network. Because the data set that we are going to have would not be too large, so in order for us not to overfitting the network, we are going to drop some columns from this table. What I'm going to do is to drop most of the columns, but just keep open X, close X, and open Y, close Y, and year and month in the table. So I'm going to drop the high X and then the access equals to 1 in place true. Similarly, I am going to drop the low X and the adjust the close. And also the volume. So this X is for the Hansen index. I'm also going to drop the high Y, low Y, adjusted close Y, and volume Y. That is for the Shanghai index that we have in the table. Okay, now we have a simpler table. And the next thing that I'm going to do is to convert all these 4 columns back to a numerical. So pandas already have a functions that can help us to do that. And that is the doc to numerical. And then we are going to convert it back to numerical value. The error that we raise here is use the chorus, and it means that if there is any value that cannot be converted, then we will just set it as a NaN. So we have 4 columns that need to convert back to numerical. So we have open Y, close Y, good. Now everything is in numerical in this table. The next thing that I'm going to do is to drop the NA functions. You use the drop NA function to drop all these NA, drop all the rows that contains NaN. So we are not going to have any rows that contains NaN after using the drop NA function. So you can see that the NaN are all gone. And because the data set that I have is too large for 30 years, so most of the data becomes non-stationary, and that would create problems when we are developing a neural network. So in order for us to avoid this non-stationary time series issue, so what I'm going to do is that we set all these years that is less than 2015, I'm going to just drop the row. So here, I'm going to use the year columns to set the criteria. So I only keep I only keep the samples if the years is larger than 2015. So now we have about 4 years of the data from 2016 to 2020. So the next things that I'm going to do is to use the previous open price, close price of the Shanghai index and Hang Seng index to predict the opening price of the Hang Seng index in the next days. So I'm going to use the previous 5 days informations to predict tomorrow's open price. That means I'm going to use these 5 rows to predict these open price in the next day. So that means I have to create a feature table that contains all these previous 5 days informations. And I also need to create a vector that contains all the labels here. So let us create the features table first. So what I'm going to do is to create 5 times that. And this is the t minus 5, that means previous 5 days information. And I will extract everything from everything in this row. And then I'm going to reset the index in order for us to use the concat function later on. So the next things I still need to create 4 additional steps. That is 4, 3, 2, 1. That means these are the informations that I'm going to collect, except the years and months. So here I use the negative index to take that out. And then I need to shift it a little bit. And so the next thing I'm going to do is to concat everything into a features table. So I have these 5 step, 4, 3, 2, 1, and then assets is equal to 1. That means I'm going to concat them side by side. Let me print out the features to show you what I have just done. So dot head 6. And here you can see that this is the original tables that we have. As I mentioned before, I'm going to stack it side by side. So you can see that the row 0 right now contains all these informations. This is the first row here. And then I extract these second row, the open price and close price for the Hang Seng Index and Shanghai Index side by side, put it in the first row. And you can see that is here. And so this is the time t minus 4, and then time t minus 3, time t minus 2, and time t minus 1. So you can see that everything is put it side by side and combined into a features table right now. The next thing that I need to have is the label vector that is starting from this value to the end. So what I'm going to do is to get the target. That should be the ILOC starting from the 5th element to the end in the first column. So again, I just reset the index. And let me show you what we have here. And here you can see that we just extract from the original combined tables, that is 19997, starting from 19997. That is the labels and that is the targets that we want to predict. And then till the end of this database. And Now the features and targets are ready. So what I'm going to do in the next step is to use sklearns to speed the data for our training. So before that, we need to extract the value from the features table first and assign it as a x here. And similarly, we just extract the target dot value from this target data frame. And now we can import sklearn model. Model selections imports the train test speed functions to help us to speed the data. So what I'm going to do is to just xtrain, xtest, ytrain, ytest. There will be 4 sets of data that we are going to have. That is the training data from these features and testing data from these features, as well as the training data from these targets and testing data from these targets. So we just use the train test speed function and then input x, y, and then the test size that I'm going to use is just take out 10% of the data for the testing set. So random seed here is that we just use, say, for example, 1, 2, 3 for the random status. It would be a very good habit to set a random seed so that later on, if we want to get back these random sampling, we still can use the same seeds to extract that. And after using this train test speed, all of the data right here, xtrain, xtest, ytrain, and ytest will be under a NumPy array. So right now we need to import NumPy as NP. And then in order for us to use the NumPy functions to normalize our data, and because I'm going to use zero mean unit variance normalization, so I need to calculate the mean and also standard deviations from these data set. So here we have the mean. Remember that we need to use the training sample to calculate the mean. X equals to 0. That means use the columns to calculate the mean. Also standard deviations, I just use the xtrain to calculate the standard deviation. And then we calculate we normalize it. Xtrain equals to xtrain minus mean over standard deviation. And similarly for the test set, we need to use the same mean and same standard deviations to do so. So finally, we can start creating our network architects and also assign the hyperparameters. In order for us to do so, we need to import few libraries from Keras. So we need to import a Keras model, import the sequential, and we need to import keras.layer, import dense layer, activation function, And we also need to import the Keras optimizer. So sequential just means that you are going to create a model that is layer by layer, which is useful for most of the problems. And dense just means that you are going to have a fully connected layers. And then activation is for the activation functions. And then optimizer is for the learning algorithm. So first of all, we need to initialize our model and by assigning it as a sequential, and then we just use the add functions and tell them that we are going to add a fully connected layer. We are going to have a 64 neurons for this layer. And then for the activation function, I'm going to use value. And then for input shape, this is just for the first layer. So we are going to have the number of features, that is the input shape. So what is n features? N features is actually the X training data dot the shape of training data, that is the number of features for it. And then 0 is actually the number of samples, but we just want to tell the models that we are going to have this number of features that is passing into this first layer. And then the second layers that we are going to have is another dense layer that has again 64 neuron, and then the activation function, again, that is a value. So we are going to have two layers, and finally we are going to add a output layer because we are going to predict a continuous values, which is the open price in the next day. So we are going to have one output, and dense layer just means that it is going to be a fully connected with just one single neuron. And then the activation function by default, that is a linear. So because we're going to predict a continuous value, so by default it should be fine. For the learning algorithm, I'm going to use a RMS pop, and we can tune the learning rate right here. Let's say, for example, we are going to have 0.0001 learning rate. And that's it. So we just created a neural network with two hidden layers, and both of them are just have 64 neurons, and also use the activation function value. And then we have a one neuron output layer, and the activation function is a linear activations. And we also use an optimizer, that is the learning algorithm that we are going to use our MS POPs for this training. And then now we can compile the model. But before that, I want to import another library from Keras, that is the fallback library. And then we are going to import the model checkpoint and also the early stopping functions. Early stopping is used for the regularizations, and this is used to set up the early stopping criteria in order for us to avoid overfittings or overtraining the neural network. And model checkpoint is used for saving the models that for each of the epoch. So to train the model, we have two steps if you still remember. The first step is the model dot compile, and then dot compile. And then the next step is the model dot fit. So there are three parameters that we need to input for the compile functions. So first of all, we need to set up the optimizer, that is the RMS pop that we are going to use. And then we also need to provide the objective functions, that is the loss functions. We are going to use MSE to as the objective functions. And then finally, we are going to use the MAE, mean absolute errors, as the evaluations function. And then the next thing that is that we are going to input for the bit function. There are a couple of things that we need to input. So first of all, we need to give the training set to it. That should be the features. And then we should give the training set for the label and validation speed. So we are going to speed it like around, so for example, 0.1. We are going to use 10% of the data for development set. So say for example, for the epoch, we are going to use 10,000. And then we are going to have a callback. I will set it up later. So say for example, callbacks equals to callbacks here. And then we also need to consider the batch size, because the training set right now is not so large, so we can just use batch size 1. We are not going to uh, have a smaller sample or have a smaller batch for training. That means we are just going to take up the whole training set for calculating the loss. So let's set up the callback function. So we are going to have a callback that is equals to a list, that is the early stopping. What we are going to use is to monitor the validation or development set losses. So if there is no further improvement for 15 steps, then we are going to stop the training. So the next thing that we need to set is for the model checkpoint. So we need to give a file path to it. And then we also need to provide a monitor. That means what we are going to monitor under this checkpoint, we are going to monitor the losses, that is our objective function. And then we save only the best model, true. And then mode equals to mean. That means that we are going to minimize, because MSE is the minimization here. That is the loss function, because we are monitoring the MSE. At the same time, this mode is an minimization. I mean, the objective is minimization. So we just put the mean here. And for the file path, you just need to provide a path to it. And also you just need to provide what kind of informations that you are going to use for the file name. So I'm going to use that for each of the epoch. I'm going to record the number of the iterations during that time for that model. And I'm going to also record the loss, the validation loss, the MAE, and also for the validations MAE. That means, so in this path, I'm going to record all the errors and as well as the number of the iterations at that time, in such a way that when I go back to the file path, I still know what kind of performance that we have for that neural network. When running the fit functions, Keras maintains a so-called history objects in the background. The objects keeps all losses values and also the other metrics values in memory so that they can be used later on for visualizations. So here we can just put a history equals to the model in order for us to store this history object. To visualize this history, you can just use the matplotlib, or here I use the Plotly to visualize them. But because this is not the most important thing, so I just copy and paste the code here in order to show you how to visualize this history data. And that's it. Now we are ready to train the neural network. Here I forget to put the curly bracket here. So let's train it again. After about 170 epochs, the models converge. And here you can see the loss value for the training set, which is the MSE that we used it. And also here you can see the mean absolute error in the training set. And that is the metrics that we assign. And there are two additional values. And the first is the validation loss, and the second is validation mean absolute error. And the first one here is actually the MSE in the development set. That is the error in the 10% sample that we spit out before. And the second value here is the MAE in the development set. To have a sense of how well and how bad our model performs, we can go back to the plot to see whether the MSE drops nicely and whether there's any issues in the bias and in the variance. In addition, remember we use the performance as the file's name for saving the models, so we can also go back to the folder to check the file names to see whether the MSE and NAE drop nicely. By doing so, we can have a quick evaluations on the trained model with the use of the development set. For additional evaluations, we can use the testing set. We memory split with the use of a function in sklearn before, and in this very last step, we can use this testing set to perform an unbiased evaluations over our trained models. And in Keras, we can use the evaluation functions to calculate the loss value and matrix value that we assigned for the models before. So still remember that we use the loss value as the MSE and then the matrix as a MAE. So here we have the MSE, MAE equals to model.evaluate. We will use the test data for these for the unbiased estimation. So let me print out the results. So we have the MSE and MAE. For illustrative purpose, let me just run these models again. And after the training, you can see here we have the MSE and also the MAE for the testing set. And as I discussed it before, developing neural network is highly iterative. So if let's say if the evaluation in the training set, development set, or testing set are not good, we always need to go back to the previous step to fine tune our models again. So say for example, if we think the bias here, that is the loss here, the loss here, and the loss here. So These three laws are actually representing the losses in the training set, development set, and testing set. So to have a feel on how well or how bad our trained models performs, we can always go back to the training era, that is the MSE, that is the loss right here, which is represents the MSE. A high value on the loss means that our model has high bias, and that means our model is likely suffer from undertraining or underfittings. In that case, we can go back to the network architects to try to increase the size of the network and or try to increase the number of epochs or find a more complex architect. So say for example, you can increase the number of neurons for these two layers, or you can also increase the number of layers right here. On the other hand, let's say, for example, you're quite comfortable with the loss and also the mean absolute error right here, and you think the model is performing quite well at this point. In that case, you need to check the validation loss and validation mean absolute error right here to see whether you are comfortable with the error rate in the development set. And also, you can check for the MSE and MAE for the testing sets to see whether you're comfortable with the error rate. So let's say you already achieve a very low bias in the training test, but yet still have a very high variance, or you could say very high MSE and MAE in your testing set or in your development set. That means your models is likely suffer from overtraining or overfittings. In that case, you might need to go back to the very first step to collect more data, or you can go back to the network architects to work out some regularizations or find a simpler architecture. Let's say, for example, you can either reduce the number of neurons in the dense layer or even remove one of the layers here. On the other hand, for the regularizations, you can also, let's say, for example, you can set a smaller numbers for the patient. Now we come to the last part, the final model. Let's assume we are now satisfied with the results so far, and we want to combine the results with multiple models to get a more generalized result. So we can apply bootstrapping techniques here. The simplest way here is to apply for these methods is to create a for loop and provide different random seeds in the sklearn train test speed for each of the cycle. And the random seed should be right here. So what we need to do is just to create a for loop, say for example for I in range 100, and then we change this value to I here. Then we can train the models and save the model within the for loop. And finally, we can predict the results from all of these neural network and combine them, for example, averaging them as our final output. But I'm not going to show this in details in here because it should not be very difficult for you to modify a bit of the code to achieve that. For your additional information, you probably need to use low weight and predict functions in Keras if you want to use the trained models to make predictions. And that this is the end of this video. I hope from what we covered here, you should be able to master the skills and develop a nice neural network to solve your own problems. So that's it. If you have any questions or suggestions about what we covered in this video, please feel free to ask in the comment section below, and I will do my best to answer. And if you enjoyed this tutorial, you can subscribe my channel, simply like the video, and it is a great support to share this video with anyone who you think would find them useful. And thank you all for watching.